Weiguo, are you ready? Let's start.
Yes, please.
Okay. Hello, good morning, good afternoon, and good evening. This is Paul Liu from NC State. Welcome again to this World River and Delta Systems Source to Sink webinar series. And today we are very delighted to invite Professor Zhang Weiguo from State Key Lab of Estuarine and Coastal Research at East China Normal University in Shanghai. Come here talk about magnetic mineral as a tracer for sediment transport from the Yangtze River to the sea, to the East China Sea. So before I introduce Professor Weiguo, and I would like to mention again, this talk number as 121 talks since August 2020 during the pandemic. So this is become a great resources. It's all previous talks have been archived on our YouTube channel and also Bilibili station. Please feel free to use them as teaching and research materials. And at the same time, we also maintain a Source to Think Twitter account. As you can see, we will announce the weekly webinar information and also sometime new publication or any related world, river, and delta related news announcement. Please following us on Twitter. And so today is the last talk before the summer break. So in next month, July, we will take a summer break. Many people have vacation, have travel, and field work. We will come back in the end of August. So our first talk after the summer break will be George Xue from Louisiana State University. Come here talk about the regional Earth system modeling platform. And then as you can see, we have already scheduled some talks, but there are also some slots available. Please, if you, your colleague, or anybody want to give a talk, please contact me. Just send me an email and we will try to schedule your talk in either September, October, or November this coming fall semester. So Professor Weiguo, as I mentioned, is currently full professor in the State Key Lab of Estuarine and Coastal Research, East China Normal University. And he graduated from over there, East China Normal, got a bachelor and PhD over there. His research mainly focused on geomorphology, sedimentology, coastal environmental change, and the tool he used is environmental magnetic chemical radionuclide OSL dating method. So I think Professor Weiguo, now is your turn. Please share your screen.
Okay, sure.
Your talk.
Okay. Okay. Can you hear me?
Yes.
Can you see the screen? Okay, good. Good morning, good afternoon, and good evening. Thanks Paul for inviting me to give this talk. And it's my pleasure to share my recent research works with my colleagues and my students. Mainly is working on the Yangtze River delta and the coast near the Yangtze River mouth. My research background, I'm geography trained by geography, and when I do my master degree, my supervisor just introduced me into the field of environmental magnetism. That is in the 1992. Okay, at the time, I just started to know a bit about environmental magnetic. Okay, so today I will just use the Yangtze River and the Yangtze River data as an example to show how magnetic mineral is a powerful tracer or powerful tools for us to study sediment transport, sediment deposition at different time scales. So first, I just mentioned briefly what is environmental magnetism. As we know, magnetic method has found a range of application in earth science, such as paleomagnetism. So environmental magnetism, this word, simply we can say is using magnetic methods to characterize magnetic minerals contained in the sediments. Okay, the magnetic minerals is mainly composed of iron oxide, such as magnetite, hematite. So this is all different kind of iron oxides. So why study magnetic minerals? Because they are widespread in the environment. Also, we know iron is coupled to carbon, coupled to sulfur in the biogeochemical processes. So these magnetic minerals has drawn attention from the magnetic study, from the geochemical studies. So we just use these magnetic minerals as a tool to study environmental problems such as sediment source tracing, environmental pollution, paleoclimate change. There are quite a lot of application of magnetic methods in earth science. Another advantage of magnetic study, because it is simple and it's cost effective. So this is quite important because like the instrument, this is a magnetic susceptibility meter. It's quite small and it's portable. So when you do field work in the field, in the daytime, you can sampling. Maybe in the evening, you can, when you go back to the hotel, you can continue with your study, use this portable instrument to measure some simple parameters, and it's very easy. And there's some maybe is a more advanced instrument, maybe you can do it in the laboratory, but this sample size is not now. Some of the instrument is quite sensitive. So if you have some several hundred microgram samples, maybe it's enough for us to study sediments, okay? So there is some important books or papers. Here I just shown this paper published in Science. It's published in 1980s. So you can know the title is saying environmental application of magnetic measurements. So this is something, a kind of a summary of the work has been carried out in the 1970s, okay? Mainly by UK scientist, Lawyer Thompson from Edinburgh University, and some from the University of Liverpool, Frank Oldfield. So they later, Lawyer Thompson and Oldfield Frank, geophysics and geographic, this is geographic, they collaborated and they published this book called Environmental Magnetism, published in 1986. In this paper, you can see this graph. This graph is just showing something like the topic we talked today, source to sink. The magnetic minerals from the rock when it is weathering, forming soil, and when the soil is eroded to the water, maybe transported by the river, transported down to the sea, or maybe it is temporarily stored, sediment stored in the lakes, and they later maybe flushed out into the sea. Another pathway of the sediment or soil maybe is carried by the atmosphere and dust, and also it can through the transport maybe also can enter into the sea. So this is a simple, another example of this source to sink, of this cycle of magnetic minerals in the Earth, in the surface Earth environment. So today, I just use this method to contribute to the study of the river delta shelf sediment source to sink studies from the Holocene time scale to the modern environment scale. So my talk focus on 4 keywords. So here, one is the source and the sink characterization of the sediments. Okay. Second, I talk to the sorting, just hydrodynamic sorting because of the particle size effect. And the third, I talk about when the sediment is buried on the seabed, it experiences post-depositional diagenesis. So this is we call it barrier. And as the fourth, when of the sediment is exposed to the air, maybe the sediment will subject to subaerial oxidation, or we call it petrogenesis. All these processes will have an impact on magnetic properties of our samples, and we can use the information obtained by magnetic methods to trace environmental processes happened in the past. The first, we talk about, just give some example of the source and the sink characterization. This map just showing, this is the Yangtze River. Yangtze River is about 6,300 kilometers long. So it's quite a large river. So when we talk about, when the sediment, this is Shanghai, there's a river mouth of the Yangtze. When we talk about the sediment of the Yangtze River, actually it is a mixture of sediments from different tributaries of the Yangtze River. Namely, some large tributaries of the Yangtze River, including, this is called the Jinsha River. So from the upstream of the Yangtze River, here is a site, a location, a city called Yibing. Okay, so this is upstream of the Yangtze River. Another tributary is called the Jialing River. It flows through the Sichuan Basin in the central, in the middle part of the China. This is the Jialing River. Another large river is the Han River. Okay, this Han River joins the mainstream of the Yangtze River at Wuhan city. Okay, so you can imagine if sediments from different sources, different tributaries have different proportions, it changes with time, we will expect the sediment arriving at the river mouth will also changing with time. Maybe this change maybe is caused by climate change or by human activities. Okay, so we need to characterize these major tributaries, and also we have the Yellow River flowing to the sea. But in the past, during the 20th century, to 19th century, the Yellow River shifted its course, the southern part to this here, and enter into the sea at the Jiangsu province here. Okay. So this diagram just showing Jinsha River, Jialing River, Han River, and the Old Yellow River. Okay, this one. So from this one, just 2 parameters here. You don't need to if you are not familiar with it, it doesn't matter. We just remember this is a concentration related parameters, and this is a mineralogy related parameters. We can see these 3 tributaries of the Yangtze River is quite different. The Jinsha River is most magnetic. It's much higher values than the other 2 tributaries. And this value is also much lower than other 2 rivers. So this is 3 tributaries of the Yangtze. And this is the Yellow River. The Yellow River, Old Yellow River, and the modern Yellow River, they have their sediments from the Chinese Loess Plateau here. So the Loess is quite a mixed sediment. So you can see the Yellow River sediment also is quite different from the tributary of the Yangtze River. So this is forms the basis for us to trace the sediment source from different areas. Okay, here these different magnetic properties of different tributaries is due to controlled by the rock types in the catchment. For example, this is the Jinsha River. We can see here the basalts occurs in this basement, in this sub-basin, and the basalt is a strong magnetic the rock type, so it leads to a much higher magnetic concentration in the sediment. And the Jialing River, it is in this basin a lot of occurrence of red beds. The red beds is contain higher content of hematite. Hematite, so it's we call the antiferromagnetic mineral. It's different from magnetite. So this is why we can see the difference of the different source. Okay. This is another example which just showing the Yangtze and the Yellow River is quite different. Okay. So this map just showing high concentration, high magnetite proportion of the Yangtze River in comparison to the Yellow River. So just give us an advantage if we want to differentiate sediment is coming from Yangtze or Yellow River. If we have samples from the continental shelf of the marginal sea of the China, this maybe is a potential tools. Okay. Also, if we separate the bark sample into different particle size, we can also see the difference between the Yangtze and the Yellow. And you can see for this parameter, we can see with decline particle size, hematite content increase in the Yangtze River. This is in contrast into the Yellow River. In Yellow River, with decline particle size, it's a pathogenic magnetite. So this is an example of the climate and rock type will control the magnetic properties in the sediment. Okay. Then we use this method to study the sediment source of the Jiangsu province. This is the coast plain of the Jiangsu. This is the Jiangsu province. So this coast plain is bounded by the Yangtze River in the south, the Yellow River in the north. And I just mentioned before, in the last 1,000 years, the yellow river has its course shift to the south, and with the older river mouth located here. Okay, so there is quite a lot of evidence saying when the Yellow River discharged the sediment into the Jiangsu province, the huge sediment discharged by the Yellow River has a significant impact on the coastal plain development of the Jiangsu plain. Okay, but we also know for the Yangtze River sediment, whether the Yangtze River will go transport northward to the Jiangsu plain. So this is an interesting question. So for, using our method, and we combine magnetic method and the geochemical method, we defined the Jiangsu coastal plain into 3 zones. So we find a Yellow River dominant northern part of this coast plain, and a southern part is dominated by the Yangtze, and there is a mixed zone between. From this map showing here, we can see the northward delivery of the Yangtze sediment into the Yellow Sea is quite limited. But the Yellow River has a quite large impact in the spatial extent for delivering sediment southward. This is related to the local hydrodynamics, as the past study has shown a dominant longshore current southward flowing in this region. Okay. Then we also just studying, this is a modern process. And when we look back to the delta evolution over the history times, this map is, this is Shanghai here, and this is the modern Yangtze estuary. And this is the northern part of the Yangtze Delta. And this line here, black line, just showing the Ming Dynasty of the 16th century. So this land just means it forms over the last 500 years, is mainly formed in this period. So for this land formation, is the sediment all comes from the Yangtze River? Is there any other additional sediment contribution from the Yellow River? In the past, some historical geographic studies has suggested the Yellow River, when the Yellow River shifted the course to the southern, to the Jiangsu province, their sediment can be transported southward and contributed to the delta formation of the Yangtze Delta, but no sediment compositional evidence. So we just wanted to check whether this hypothesis is correct. We did age with a dating of the sediment from the core here, and we can see around the water depths about 18 meters, the sediment is largely formed, have an age of about 2,000 years. But then the sediment is largely formed in last 500 years, okay? So this is just showing the sedimentation rate. So you can all see these cores have a rapid sedimentation rate happened in the last 500 years, okay? This is 500 years. And then we have the 3 cores, and this core is from the southern part. This core is from the northern part. We can find in this such a small area, the sediment from different cores are showing difference in magnetic properties. So we can see the northern side, there's a core called Wangbao, has no magnetic mineral concentration and low S ratio, S values than those of southern core. And this is using zircon uranium-led geochronology studies also supports such a compositional difference between sediments from the southern and the northern part. And then we do the principal component analysis. And we also compared the sediment, the three cores here. We compared their sediment composition, not only with the Yellow River, but also with the tributaries of the Yangtze River. We mentioned that Jinsha River, Jialing River, and Han River before. And this map just we divided the sediment into four classes, less than 16 micrometer, 16 to 32 micrometer, and coarse silt and sand. Okay, and from this one, we got an impression. We suggest the sediment have two sources. Some is from the Yangtze River, some is from the Yellow River. And the Yellow River has more influence on sediment from the northern part, but the Yangtze River has more influence on the southern part. This is our story. Then we linked such a story to the climate change and the historical war, okay, happened in China. First, I should mention the southern shift of the Yellow River. It is not a natural one. It is due to war. It's how to say, it's a man-made shift of course, because at the time, we call the Song Dynasty, they just shifted the Yellow River core to want to stop the invaders from the northern romantic troops, okay? And so this is happened in the last 1,000 years. But we know the last 500 years, we have the Little Ice Age and the modern warming climate. When the Little Ice Age, the China is a monsoon climate. We have a strong winter monsoon. The wind is northern wind, northern wind, okay? So this way we just say strong southward coast current and carry more Yellow River sediment to the Yangtze Delta and called rapid aggregation of the delta. And when the enough sediment accumulated in the delta, emerged shores and then land reclamation and coastal progression, then we see the present Yangtze Delta. Okay, so this is just an example. We just I think the Yangtze River Delta is also unique because it has a large river on its northern side. Okay. The second, I wanted to talk about the sorting. Okay, sorting. So just when we return back to the tributaries of the Yangtze River, when we sample the sediment and separate the bark sample into different particle size, we can find different particle size. They have different magnetic properties. It means the magnetic minerals contained in different fractions of the sediment is different. Okay, so this is it means when the sediment is transported from the upstream downstream, when the particle size there is called sorting, maybe coarse particles set down first, and the finer particles transport downstream. So we can see the signal of the source will be changed on the pathway from the source to sink, okay? So this parameter is a magnetic grain size of the magnetic minerals. It also shows with the increase in particle size of sediment, the magnetic mineral contained in the different particle size also become causal, okay? This can be expected, okay? This is just showing the example in the Yangtze estuary. We sampled the suspended sediment and the bottom sediment on 3 transects. Okay, this is from the inner estuary to the river mouth from this side. So from these 3 transects, this open circle is a suspended sediment, and the solid circle is bottom sediment. So we can see from the inner part of the estuary to the mouth, there is an increasing of this parameter, just indicating particle grain size of magnetic mineral become finer downstream. So this is downstream, just means it can indicating the sediment transport direction, okay, from this part to the outside, okay. When we go to East China Sea, this is we collect the surface sediment samples in May and in August. Okay, we collect the surface sediment sample, and we also we measure the magnetic properties, and we also measure the radionuclides like lead-210, and this kind of, they can also be used as a particle transport indicator, okay? Here, I just showing this parameter, as I mentioned, you can see it shows some alongshore trends it indicates grain size of magnetic mineral become finer alongshore, and also there is some close sheaf transport of this magnetic mineral, and this kind of this is in May and this is in August. Okay, so all this it means in different season, different months, the sediment transport direction is also changes with time. This is related to the water discharge of the Yangtze River. Okay, in August is the flooding season of the Yangtze River, and the physical oceanographic study has shown in the August in the summer season there is a northward transport of the Yangtze River diluted water, northward transport. And in winter season, is mainly southward transport. So our magnetic method also supports this one. And this is another example from the Red River in Vietnam. So this is from the upstream down to the delta, down to the subaqueous delta. And this is similar, this parameter, you can see from the subaqueous delta. Okay, this line should shift here, shift this one. Okay, it's an increased trend from the near shore to the offshore with the increase in depth. We can see this transport direction. And this one just showing another river called Jiang River, O River. This is the Yangtze River estuary. This is Hangzhou Bay, and this is the O River. This O River is also tide influenced estuary. So here we can see fluvial reach and tidal reach, and also in the tidal reach we can see this trend, this increasing of this magnetic parameter, indicating fining of the minerals. Okay, so it just mean this sorting phenomena is widely occurring in the environment. So when the magnetic mineral composition is changes due to grain size, due to hydrodynamic sorting, we can imagine the composition of the sediment will also be changed. So sometimes we need to make some compensation for this kind of particle size effect. And if we measure this parameter, we can just know how is this sorting effect on the composition of the sediment. Okay. The third, I will talk about the barrier, sediment barrier. When the sediment deposited on the seabed, and then it will experience post-depositional Diagenesis. This is an ideal Diagenesis zonation in sediments. Okay, different electron acceptor and chemical zone, and you see here ion mineral formation, hematite, magnetite, and then with increasing depth, we can see from oxidizing condition to reducing condition, we can see from magnetite dominated sediment into pyrite, iron sulfide, and greigite, something like this one. Okay, this is an ideal zonation of sediment, but in reality, this zonation may be disturbed by bioturbation. Okay. And when we study the subaqueous delta sediment, if we dating sediment deposition rate in the last 100 years using short-term radionuclides, we can see the sedimentation rate in the delta is different spatially. Here is the depot center with 3 to 5 centimeters per year, but this deposition rate will decrease offshore. Okay, and in this part of the inner shelf mud, we have 1 to 2 centimeters per year, and in the northern part, here is illusion. No recent deposition over the last 100 years. Okay, and when we take a sediment cores from the different parts, we can see here. This is called magnetic susceptibility. And from this zone, this part with relatively high sedimentation rate, we can see this value is almost homogeneous, no significant, no marked changes with depths. But in this part with slow or low sedimentation rate, we can see there is a zonation of these parameters, a high value in the upper part, and a transitional part, and a low and the part in the lower part. Okay, and if we go to into this region, we can see homogeneous again, but compared to this one, this value is almost half of this one. It's different. So our explanation is this one actually corresponding to this part. It means the original magnetic minerals is modified or changed due to reductive diagenesis. So then if this one, it should be occur in a deep zone, but if it is exposed on the surface, it means no recent sediment deposition in the past. And this is an old sediment. It's not a present one. If it is a present modern sediment, we expect it should have a similar value like this one, okay? Because short-term radionuclide dating can give you an age of 100 years. So if the age is much older, we maybe use OSL dating, okay? So here you can show you two cores. This core is a modern sediment deposition here. Susceptibility is high, about 60, and the age is something 100 years and 200 years, okay? And this one is this parameter is quite small, between 20 and 30, and the dating give you an age about 2,000 years, okay? So this is nicely, it shows the effect of Diagenesis magnetic properties. And we can use this information to infer sediment ages relatively, okay? So in the Yangtze Estuary here, this channel bed has a scoring in the recent years due to hydrodynamic changes. So you can see this blue color means erosion, and the red color means deposition. Okay, there's erosion here, and this erosion, we can imagine it exposed the older sediments directly onto the seabed. Okay, and when this sediment is resuspended into the estuary, it will mix with the modern sediment. And so actually, if you sample the sediment in the Yangtze Estuary today, it is quite possible. It is a composition of both of the modern sediment and old sediment happened. Is due to erosion. Okay, so why we this is because this old sediment, as we mentioned, it has a magnetic properties different from the modern one. Okay, and this Diagenesis also happens in the inner shelf mud of the East China Sea. Here we have 3 cores along a transect along these 3 cores here, and this inner part has a higher sedimentation rate than in the offshore. Using this is lead 210 is not successful. It is quite normal. Okay, I think, but this season can be used this marker of 1963. We tentatively agree this is 1963. Okay, we got the sedimentation rate here. You can see higher sedimentation rate in the onshore, in the inner part, and offshore is much lower. And we can see susceptibility is also homogeneous one in the inner part, but in the offshore we can see the zonation just similar to the we observed in the Yangtze Estuary. Okay, this is zonation. So this is the zonation just means offshore decrease in sedimentation rate, and we find this transition from homogeneous part to a decline part. The transition, maybe this one, something happened here, the depths. Okay, but if we move the further south, like here, if we move from here to this one, to further south, okay, we have several, someone is studied by our group, someone is by colleagues from Tongji University. So if we compare the susceptibility, this is a volume magnetic susceptibility, this is a mass specific susceptibility. So you can just see this value from a high value rapid decline zone and a homogeneous one. And this one is much thinner than our the 3 core in the more closer to the Yangtze estuary. So this one is also indicating higher sedimentation rate for the inner shell of mud near the Yangtze River's mouth, and further away from the Yangtze River estuary, this one becomes shallow and indicating a decline in sedimentation rate. This is a general one. Okay. This is just when we see reductive Diagenesis causing magnetic susceptibility become lower is due to destroy of magnetite. And another mineral we call the greigite. It is like have this form, and this greigite they think it is incomplete pelletization product before the formation of a pyrite. Okay, so why is incomplete is due to iron or sulfate input limit. Okay, and if this sulfate input limit maybe is related to salinity change, because we see seawater has a higher sulfate content than fresh water. Okay, so if we have salinity change maybe caused by fresh water and marine water mixture, so when the environment is a non-stable environment, so maybe we can have this mineral formation in our environment. So this one, in the Holocene deposits in the Yangtze estuary, we have 3 cores here. And this course has something like 50 to 60 meter. The Holocene, okay, deposit is quite thick in the Yangtze estuary. And you can see in the lower part is a transglacial deposit. And in the upper part is a reglacial deposit. And in the reglacial deposit, you can imagine the salinity will be low because of the fresh water discharge and the sediment discharge, because of and in this transglacial, we can imagine the salinity will become increasing from a fluvial environment to a marine environment with this process. And we did the dating, and we find that these 3 cores, and this green shade is marked this mineral, and these minerals we can find is mainly occurring in this zone C, unit C. This unit C has a rapid deposition sedimentation rate due to rapid sea level rise in Old Holocene. And also we find this mineral it occurring at the transboundary, like this one, between the boundary of unit B and unit A. It has this occurrence, and this boundary between unit C and unit D, it also has some occurrence. Okay, so sedimentary phase transition zone normally it is in association with salinity change, just as I mentioned, because of the freshwater influence, marine water influence. Okay, and we also did some geochemical indicators, salinity indicators, and this one of this magnetic parameters correspond well with the geochemical indicators. And we just use this schematic illustration of gray guide occurrence in a holocene environment. So we see from a tidal river to an estuary during the marine transgression, maybe at this boundary we can find gray guide. And during this estuary to the shallow marine or flow delta environment, we can also, because of rapid sedimentation rate, we can also expect a high abundant occurrence of the mineral. But in the shallow marine delta environment, is a relatively low sedimentation rate and a higher salinity, maybe more complete iron sulfide formation. And then we see a lot of pyrite here. And then again, when the salinity become low, and we see gray guide occurrence again. Okay, so this mineral, because gray guide is easily identified by this magnetic method, so it is more easy to identify than using geochemical method. Lastly, I just mentioned subaerial oxidation. When the sediment become emergent or become land emergent, the sediment will be subjected to subaerial oxidation. Okay, this cause is sampled from here, also near the in the northern part of the Yangtze Delta. From the color, you can see gray, dark gray to yellow brownish color. It means a subaerial oxidation happened here. Okay, this color also means some iron oxide formation. Okay, and we find this hematite, goethite formed during the pathogenic process when the sediment is exposed to the air. Okay, it forms this one, causing these two values become low. And this is hematite content using diffuse reflective spectroscope. Hematite and goethite estimation, you can find their content is increased in the upper part of the sediment. And so this pathogenic process is quite quickly. When the sediment is exposed to the air, we can see the rapid transformation of the iron oxides. Okay, and so this is another call from Shanghai, and you can see here. You also see the surface part of the cores have lower parameters, like we see in the northern part of the Yangtze Delta. And you can see here in the paleosoil, this is formed in the late Pleistocene stage. You can see when the sea level is low, and this part of paleosoil formed, it also has such a feature similar to we saw here. So using this one, we can also identify past formation of soil in the course. Okay, so this is another example. So in summary, I just summed here, just saying these magnetic properties can be used to study sediment provenance. But as I mentioned in this this sediment provenance tracing is influenced by particle size sorting during source to sink transport. Okay, but also is influenced by the diagenesis. Okay, and so using magnetic mineral to trace sediment provenance, we should minimize the effect of this sorting and diagenesis. So someone suggests that we should use magnetic minerals as inclusions in silicates, like in quartz, because magnetic mineral contained in quartz is protected from diagenetic alternation because of the shear of quartz. Okay, so it is conservative during transport. So this is a good way to using magnetic property to tracing sediment provenance. And we find aggregates, okay, is common in the sedimentary environment, not only in the Yangtze Delta, in the Yangtze estuary, but also in the Yellow Sea, in the East China Sea, many places we can find it. So this one normally its occurrence can indicate some fluctuating environment condition, okay, oscillating environment condition, because like a salinity change or other parameter, deposition, sedimentation rate change, this non-steady sedimentation condition maybe can lead to aggregate generation, okay? And also the pathogenesis due to sea level change or sediment coastline progradation can also leave an imprint in magnetic properties. So in overall, I think magnetic properties in combination with other methods can provide valuable information in the environment process from source to sink, and also in paleo environment reconstruction studies. Okay, I think my time is over, so I stop here. And thanks for your attention. If any question will come. This is my email. Okay, Paul.
Yeah, thank you, Weiguo. That's fantastic. This wonderful talk, and particularly you talk about the implication and also the limitation, and that's great. Okay, now we open the floor to the audience. If you have any question, please go ahead, unmute yourself, directly ask Weiguo. Yeah. Anybody have any question?
Yeah, I have a question here.
Yeah, go ahead.
Hi, this is Muhammad from NC State. I want to ask if the magnetic susceptibility is effective if we are trying to see the depth, like how much it's effective to get the depth of the formation, for example.
You mean what's the depth formation?
Sorry, the thickness. I miss the thickness of the formation.
Sorry.
Thickness.
You mean
like if it's a thin layer of magnetic formation against one thick layer, can we differentiate between them based on the magnetic susceptibility?
You mean magnetic susceptibility, the layer? You mean formation?
Yeah.
You mean it's in the sediment or in the
in the sediment?
I just how to say how maybe I didn't catch your words because of the because of the Wi-Fi, okay, online. I just think sediment magnetic mineral contained in the sediment. Some is derived from the catchment or from the upstream. Some is formed in situ or during diagenic process or pathogenic process or oxygenic processes. The formation, the age or formation depths, it is depending on the environmental conditions. Okay, so some maybe is formed. Some of the magnetic minerals may be formed if it was a secondary magnetic mineral formed, then maybe it's formed at the water and the sediment interface. Just when sediment is deposited, maybe it can formation of a new magnetic minerals. But some can be formed long after the sediment become buried. Okay, because in the underneath the sediment seabed, maybe we have some like a missing upward transport or something. So I think the formation of magnetic mineral can be happened in any stage of during early diagenesis, at least in the Holocene sediment deposition. Some is maybe formed quite new, some maybe came from the for a long time. I'm not sure I catch your words or something, but I just, yeah.
Yeah, that's good enough. Thank you.
Okay, anybody else? Yeah, go ahead if you have any question, comments, anything to Professor Weiguo. So Weiguo, you show in the last couple slides, you show, before the sea level transgression and the Paleosoil, and now it showed the similar very low magnetic signal. And during the water portion, during the high stand sea level, it's become, that's a little bit difference. But is any difference between the this portion, and did you study the what is any different this fluvial compared to modern fluvial? Is it before the how to say, before the Holocene, is a later Pleistocene, that Paleosoil is what's the geomagnetic mineral, and also is they are similar or there's some different?
Like this one, okay, you see some, they have some common feature, okay. They contain some we call the hematite, goethite. It's an oxidizing condition, but you can also see some of this value is quite different, okay. This is quite recent pathogenic processes, I think, because this part become emergent above the sea level, maybe only in the last several hundred years, I think. So at least this soil pathogenesis process happens quite a short time. But here you can see this value is much lower compared to this part. It means much more. This is called hematite, goethite minerals, and also this process is maybe is due to long-term pathogenic processes, but also it could be the climate maybe also is different, but
Yeah.
I haven't did more. I haven't did such a kind of a comparison study yet. Okay, but I assume from this parameter here, I think one factor is time. Time is important. And then I think maybe the climate change, like a temperature or precipitation, possibly also influence. Yeah.
Oh, okay. And one more question for me. Did you see the difference, the impact from freshwater, like the lake, in a freshwater lake, the sediment core, compare on the delta, the saltwater, mixed water, and also the ocean, the salt water, the seawater, to sediment to the geometric tracing or information?
We in the past we did some core in the Taihu Lake, okay, and in the Taihu Lake, some of the sediment you can also see the present Taihu Lake is a freshwater one, but in the past when the Taihu Lake is formed, the Taihu Lake in the past it is also experience something called marine water intrusion in the Taihu Lake. So you can also see such a kind of, like I mentioned, like a greigite occurrence in sediment core if you sampled from the Taihu Lake. Okay, so also my colleagues they sampled some sediment from the Salinity Lake deposit. They also can find that this Salinity Lake also have salinity change fluctuations with time, and you can also find some like occurrence of greigite, something like that one. Yeah.
Okay. Very, very interesting. That's very good.
Yeah.
Okay. Anybody else? Any questions? Okay. If not, and we give Professor Zhang thank you very much for this great talk. And as I mentioned, this is our the last talk before the summer. I hope I can you have a great summer break, and when we coming back, we will resume our talking end of August. So thank you, everybody, and I hope you have a great summer and have a great break.